everyone. Thank you for joining us today. We are FTN Engineering, and our project was the 70th Street Trolley Station Pedestrian Bridge located in La Mesa, California. Before jumping straight into the design, our team would like to highlight main stakeholders involved with this project. First, we would like to highlight the owner, which is the City of La Mesa, who we have worked very closely with throughout the entire design process. Next up, the design consultant would be our team, also known as FTN Engineering. Again, a big thank you to everyone for joining us. Next, we have the SAGE project, which was a collaborative stakeholder that really binded the communication between ourselves and the owner to ensure a sustainable design. Jumping into the project itself, the map we are looking at is the City of La Mesa, where the Lake Murray Boulevard overpasses Interstate 8. As you can see, the north side of the freeway contains a large residential community that extends far beyond the limits of this map image. With this said, the main problem that the city wanted to address is the current route residents must embark on in order to reach the trolley station on the south side of the freeway. The yellow route identifies the current legal pedestrian route, and as you can see, it is quite lengthy and averages about 15 minutes. This route includes many unsafe traffic features, the most important being the inconsiderable amount of sidewalks and their placement. With this said, our team was tasked with designing a pedestrian bridge that spanned across Interstate 8 in order to provide a safe and efficient route for residents of La Mesa that coincides with the City of La Mesa's Climate Action Plan and Vision Zero program. Before getting into the technical details of our design, I would like to present the entire FTN engineering team. Melina Gabiola, Project Manager. Callie Bola, Stormwater Engineer. Pascal Conte, Structural Engineer. Daniel Iselli, Geotechnical Engineer. Emma Lucy, Construction Engineer. Kevin O'Mara, Stormwater and Structural Engineer. Jordan Park, Transportation Engineer.
The purpose of the Transportation Impact Study is to identify and evaluate any potential transportation-related impacts associated with the construction of the proposed 70th Street Trolley Station Pedestrian Bridge. The study was divided into roadway segment impact analysis and pedestrian segment impact analysis. The three study roadway segments, as shown in the figure, are the segments that were analyzed in this study. Since we were building a pedestrian bridge, it was important to consider the possibility of a vehicle trip reduction. Per the City of San Diego Impact Study Manual, a vehicular trip reduction rate is allowable. This standard mentions that for projects planned within a walking distance of 1,500 feet from a transit station, due to San Diego's expanding mass transit system, this reduction rate may be applied. Since our project provides direct access to a transit station, a conservative 4% reduction was applied to the volumes under the proposed project conditions. The before and after level of service analysis was defined through the ITE guidelines for transportation impact studies in the San Diego region. As you can see, there actually was a significant impact due to the reduction rate. Parkway Drive went from a level of service B to a level of service C, improving the level of service with the construction of the pedestrian bridge. The figure shown presents the existing pedestrian network conditions. As seen, the current pedestrian network is simply unsafe. There are multiple crossings causing delays, sidewalks along busy streets and only on one side of the roadway, and an uncontrolled pedestrian crossing at the westbound I-8 on-ramp. This pedestrian route discourages users to walk and use the transit station. In the data collecting phase of the project, our team performed a community survey, as seen, to address concerns of the nearby community regarding traffic safety, efficiency, and potential use of the proposed pedestrian bridge. The collected results helped us assume the increase in pedestrian volumes. For all pedestrian level services, the methods and assumptions used were taken from the Highway Capacity Manual. Going into the existing pedestrian level service analysis, the peak 15-minute based on the pedestrian count that our team took was 24 pedestrians per every 15 minutes. As you can see in the tables, the pedestrian level service for the proposed bridge is A and will remain A as we approach horizon year. By using the results from our community survey, we were able to assume that if the pedestrian bridge were to be constructed, The peak 15-minute flow rate will be 40 pedestrians per every 15 minutes. This number will only go up each year as San Diego moves toward expanding the mass transit system and aligning with the region's multimodal transportation goals.
For our structural design, we decided to use partially pre-stressed concrete due to its resistance to cracking and longer longevity. Each span is different due to the unavailability of land around. Trying to find a uniform cross-section for the whole bridge for aesthetical reasons was hard, and we had to iterate multiple times due to the change in span lengths that differed between span to span.
To design this bridge, we utilized load factor resistance design. The cross-section is 6 feet deep with the properties and dimensions shown in the slide. The dead load comes from the self-weight and the additional superimposed dead load. The unfactored live load comes from the California Building Code 100 pounds per square foot, which comes out to 0.8 kips per linear foot.
For bending capacity, we utilized the equations given to us by Ashto and compared the nominal bending resistance multiplied by the capacity reduction factor phi, and compared it to the ultimate bending moment and the moment at cracking, and made sure that the nominal bending resistance was greater than the ultimate and the cracking with the respective multiplication terms in front. For simplicity of our calculations, we analyzed each beam independent of the other, making each beam a simply supported beam, and on top of that, analyzed each beam in the linear elastic region only. For deflection, we calculated all the deflections that happened instantaneous due to the pre-stressing force, due to dead load, due to live load, due to additional load, and due to the lifetime load. And they are all denoted on the slide with the following equations for the deflection upwards that leads to camber, and an explanation of what camber looks like and does.
The draping was determined by fitting the tendon within the calculated limits shown in the chart above. The draping points varied for each span, but all resembled the same shape. The tendon was placed at the neutral axis at the support, so we didn't create a secondary moment within the span. The shear was designed using the conservative method, which neglects the upward pre-stressing force. For each span, we utilized minimum reinforcement. The shear spacing was offset by 5 inches at each support, and we had alternating end conditions shown in the detail, which provide support to the deck. Each of the columns were rectangular columns that are 2 feet by 7 feet, with the 7-foot dimension acting perpendicular to the span of the bridge. One column was designed with all the worst conditions, and slenderness was neglected due to the size and shape of the column. The column was designed to support the axial load from the bridge and an equivalent shear force from seismic loads. The shear force also created a moment at the bottom of the column, which was analyzed as a singly reinforced column along both axes because we don't know where the seismic load will come from. We added abutments at the top of the column to hold the bridge in place, and bearing pads were placed to prevent rubbing of concrete on concrete, allow the joint to act as a pin, and redistribute the load from the hollow portion of the bridge.
Due to existing development, as well as the lack of equipment and scope of this course, FTN engineering was not able to investigate the soil directly on site. Instead, the geologic map of the La Mesa Quadrangle was used to find the existing conditions under our project site. According to this map, stadium conglomerate bedrock is present on both north and south ends of the proposed bridge. Geotechnical investigations of nearby locations, done by AMEC Environment and Infrastructure, were then utilized to verify the existing conditions. According to their boring logs, bedrock was encountered at a depth of 6 feet on the north end and 7 feet on the south end, with poorly consolidated alluvium and colluvium deposits on both ends above bedrock. It was found that a deep foundation design using piles and pile caps would be most feasible and require the least amount of grading for our project.
Since this project will cause a change in drainage patterns, a hydrology study was conducted to analyze the existing and proposed conditions under 100-year storm events using the County of San Diego Hydrology Manual. An important factor in determining what the peak runoff is in the existing and proposed conditions is the weighted runoff coefficient. This was calculated using C values of 0.9 for the impervious areas and 0.3 for the pervious areas shown in the table. The flow rates were calculated using the rational method. C is the weighted runoff coefficient. I is the intensity, which was found from the isopluvial maps and intensity duration design chart, and A is the total area of the project. Since the created or impervious area is more than 5,000 square feet, this is a priority development project, which means that permanent best management practices will be implemented. The County of San Diego BMP sizing worksheet was used to determine that one bioretention basin will be constructed on each side of the bridge. The area of the North BMP is 110 square feet and the area of the South BMP is 65 square feet.
We decided to separate the construction into 6 phases. We start in the north with pile foundations. This phase will require a lane closure and detour. Then we move south and do similar. After foundations, we stay in the south to set up tower foundations and the tower itself. This phase also requires a detour of not only cars but the bus stop locations. Moving back to the north, we again continue to work on the tower foundation and tower. Here we heavily rely on the north parking lot as a construction zone. Phase 5 and 6 include median pile foundation and the installation of precast concrete sections. These 2 phases require highway lane closures as well as required night work. The blue hatching represents the laydown areas being used through all phases. The cost estimate is broken up into 3 parts: substructure, everything below the ground; superstructure, bridge components above the ground, including columns, abutments, precast concrete segments, and stairs; and lastly, earthwork. The cost estimate mainly includes the prices of material and labor. The cost estimate does not include right-of-way or easement costs. The final cost came in a little under $2 million.